Hello everybody, this is the first video for Chapter 9 of the Reinforcement Learning course. So the purpose of this chapter is to introduce approximation methods to approximate the value function and make reinforcement learning algorithms we've seen previously applicable to very large problems. Okay, so in what we did previously, we had a table lookup approach where the value of each state or its approximated value was listed separately for each state, but for problems where the state space is way too large, this might not be feasible. So if you have 10 to the power 10 states, of course you cannot store a different value for each state. So we're going to see how to go around this problem and use approximation methods to handle this issue. So in this chapter, we will study the on-policy prediction problem. Okay, so prediction means that we fix the policy, we don't attempt to optimize it, and on policy means that we use the same policy to generate episodes and to have an approximation of the optimal policy. So our approximation of the optimal policy is the one used to generate episodes. All these methods can be applied either off policy or for control rather than predictions, but these generalizations will be covered in subsequent chapters. So for chapter 9, we will stick to on-policy prediction and show how to introduce approximations of the value function in this context. So this chapter covers chapter 9 from the textbook. So feel free to refer to the textbook if my explanations are not clear to you. Okay, so as we mentioned earlier, many reinforcement learning problems, they involve enormous state space. Okay, so if you play chess or if you play backgammon or if you play Go or any similar types of games, then the number of possible location of the various pieces on the board, they're enormous. Okay, so there are many other problems where this is the case. So if you deal with enormous state space, we cannot use what we call tabular methods that we've considered earlier, whereas as I just mentioned earlier, you have one estimate for every single state, and then you update the estimate for one state at a time. Okay, so this would take way too much time to optimize, and you probably would need way too much memory to store the estimate of all these states. Okay, so this is not a feasible. So the algorithms and the way they were presented earlier, they would work for small problems where the state space is of limited size, but for enormous problems, it would be problematic to use them as presented earlier. So what we will do, instead of having a separate estimate of the value of the various states, we will have an approximation, a parametric approximation of the value function, where the number of parameters is much lower than the number of states. So the problem, as we will see subsequently, will boil down to estimating the parameters of our approximation instead of the value of each state separately. Okay, so this approach should reduce computational requirements and make the new algorithms feasible for problems with higher complexity. Okay, so in very large problems, one issue we have is that almost every possible state will never be encountered in the episodes generated. Okay, so for example, if there are 10 to the 10 states possible, even if you generate, for example, 10,000 episodes or 1,000,000 episodes, the vast majority of the states will never be encountered. Okay, so how to estimate the value of such states? In that case, you cannot. So if you use previous methods, you would never have updated your initial estimates for such states, which of course would not be acceptable. So this points to the need to apply what we call generalization. Okay, so what do we mean by generalization here? It's the ability to infer the value of a state we have never encountered by looking at other states that are similar and which we've encountered before. Okay, so for example, if there's a state you've never seen before, you have no clue what its value is, but maybe there's a very similar state that is that you have encountered in practice, and for this state that you have encountered, you were able to form an estimate of it. Then maybe the value of this unseen state can be inferred or approximated by the value of a very similar state. So this is the idea about generalization, is that we need to infer the value of states not seen before from the values of states that were visited. Okay, this is the general idea. How this materializes in practice, we will see this, and we will discuss this in this chapter. Okay, so about generalization methods, these were extensively studied in the statistics and machine learning literature. Okay, so we will not reinvent the wheel here. We shall rely on mainly on existing methods for generalization. So what we would do here, or what we would need, is we need to perform function approximation. Okay, so we have a function which is the value function, which has a distinct value for all the states. Well, instead of having the true value function, we will form a parametric approximate approximation of this function. Okay, so we will select a few. We will assume we know the value of that function at a few points, and then based on these known values, we are trying to infer the value of that function for all other unknown points. Okay, so this topic is known as supervised learning in the machine learning literature, or regression, for example, in the statistics literature. Okay, so for those who did the statistical learning class, this is extensively discussed, but if you did, for example, only a linear regression class, you can see what that this method could be applicable in that case. Okay, so linear regression, you have noisy estimates of the value of a function, of a linear function at various values of x, and then you fit a curve or a straight line across these points to approximate the value of the linear function at all other unknown points. Okay, so here this is the same thing we're going to do here, except we won't consider necessarily linear functions, but we might consider nonlinear approximations, nonlinear parametric approximations. Okay, so the main topic of this chapter is in fact to introduce these approximation methods where we will approximate the value function based on some parametric approximation, and we will introduce these approximations into reinforcement learning algorithms. Okay, so the algorithms we will present, they're inspired from what we've done in the previous chapters, but we will slightly modify them to be able to adapt them to provide them the ability to use function approximation and make them applicable for very large problems. So as we mentioned, this chapter exclusively focuses on the on-policy prediction problem. For the control problem, this is covered in subsequent chapters. And for still off-policy methods, this is covered in the textbook, but we won't have time to go extensively through them. So for off-policy control methods, this is left out of scope of the current course, and you can refer to the textbook for this topic. Okay, so prediction problem means we have a fixed policy pi and we want to estimate the value function of that policy. Okay, so here, as we mentioned previously, for the current chapter, the value function is represented or approximated not by a list of values, so not as one value per state, but instead as a parametric function with parameters. We will call them either parameters or weights. Parameters or weights embedded in the vector W here, which is d-dimensional. Okay, so we will use the following approximation that the true value function for our policy pi in a state S will be approximated by the parametric function v hat, where with parameters W. Okay, so what could be here that v hat? Well, and what would be these W's? So these this function v hat can be many things. Okay, so for example, we could have v hat being a linear functions, and here the W's could be the intercept and the slopes of that linear function. V hat could be an artificial neural networks, and W could be the weights of the neural networks. So for those who did statistical learning, V could be a decision tree, and here the W's could represent the various cut points of values for the tree and the various decision variables for the tree. So we can see V hat can be many types of function, and W are simply the parameters characterizing this function. So what this entails doing here is, instead of learning the values for each state separately, we will try to learn what values of the parameters could best approximate the true value function. So why is that of interest again? So typically, the dimension of the vector W, which we call D, is much smaller than the total number of states. Okay, so if you have 10 to the power 10 states, well, your parametric approximation of the value function shall not have the same number of parameters. Otherwise, we would still have the same problems where we have too many parameters. And so you can think maybe W has 1,000 parameters, or maybe 10,000s, or maybe 10. But the dimension of the parameter vector is much smaller than the number of states, so we have much less parameters to learn, and this makes the problem much more tractable in practice. Okay, so using approximation methods for the value function, it will reduce the dimensionality of our problems because we have less information to learn. Okay, this of course it's at the expense of losing some precision, because sometimes the best parametric approximation of the value function is not exactly the true value function, but this loss of precision or accuracy will be needed to make the algorithms work. So now one key issue or key feature of the algorithms which will change by introducing approximation is the following. Okay, so in algorithms of the previous chapters, the tabular algorithms, when we modified the estimated value of one state, the estimated value of all other states did not change. Okay, so you adjusted the value of a single state at a time. Now, with approximation, you cannot do that, because the parameters are driving the values of many states at a time. So it's not one parameter by state, because there's way more states than parameters. So each parameter must impact simultaneously the estimated value of many states. So whenever you adjust a parameter or you learn the value of a parameter, parameter, sorry, I always say parameter, but I should say parameter. So when you modify the value of a parameter, you're going to impact your estimate of many states at a time. Okay, so this is different from what we've done previously. Okay, so this has advantages because, of course, if you only adjusted the value of one state at the time, you would never go through all states, so this isn't feasible. But this also can have unfortunate effects, which is that sometimes you observe a state, but you will, when you modify the parameter, you might adversely impact your estimate of other states that are less similar or less relevant, and this might be problematic. But this is how it works. Okay, so first we said V hat can be many things. It could be a neural network, can be linear functions, it can be like polynomial functions or many other things. But we must ask ourselves what would be suitable choices for this. Okay, so the parametric approximations we will consider should have the following properties if we want to use them in a reinforcement learning setting. So first, parametric functions we choose should provide the ability to learn incrementally. Okay, so in many instances, reinforcement learning occurs when some agent is interacting in real time with the environment. Okay, so this way of learning is called online. So online means you learn as you interact in life. Okay, so you have a live interaction with your environment, and whenever the outcomes occur, you use them to update your knowledge. Okay, but as we saw in previous chapters, the learning is done incrementally. Okay, so every time you observe a new information, you slightly adjust your estimates of the value of the states. You don't want to have a very large leap every time. Okay, so to have small adjustments, we need functions that, parametric functions that can be slightly modified every time new information is available. Okay, so if the functions cannot have this flexibility to be slightly altered at the time, then they might not be good candidates for reinforcement learning. Another reason for that is in many problems, the functions should be able to handle non-stationarity. Okay, so the reason for that is if you apply your algorithms to control problems, then as you refine your policy, your associated value function is changing through time. Okay, so as you improve your policy, the associated value function with that new learned policy changes, and as it changes, your value function estimate should be able to change accordingly. Okay, so it'd be sufficiently flexible to be able to change through time. Okay, so in a nutshell, although in theory we could take any function for that, many choices of functions might be bad because sometimes if the functions are not flexible enough to be altered smoothly, successively, without having drastic changes, then they wouldn't be good candidates for reinforcement learning. Okay, so polynomial functions, neural networks, etc. These functions are well known to allow for the possibility of small adjustments at the time, which is a desirable property when used in reinforcement learning settings. Okay, so a bit of notation to explain what we will do subsequently. All the previous algorithms seen in previous chapters could be represented by the following notation. Okay, so S arrow U means the following. We update the value of a state S by using the target U. Okay, so for practically all, or even all algorithms seen earlier, every time we observed some new information, so the end of an episode or a new reward or something like that, then for one state, we shifted the estimated value of that state slightly in the direction of what we call the target. Okay, so you here that is the target. What were the targets? So for Monte Carlo algorithms, the target were the full return of the episode. Okay, so Monte Carlo settings for whenever facing a state st at time t, we modified its value incrementally in the direction of the return at time t. For TD methods, the algorithms were of the following form. So the state encountered at time t had its value slightly shifted towards the target, which was here the next reward plus the discount factor times the bootstrapping term here, which is the estimated value of the successor state. For dynamic programming methods, we had algorithms of the following form. So the value of some state S, any state S, was updated through, this is the, value iteration. So, not value iteration, but policy evaluation algorithm, the value of a state was updated by the expectation under the policy pi of the next reward plus the discount factor times the value function at the successor state given you currently are in state S. Okay, so here if v pi is known exactly, you can plug v pi here, but for many algorithms it should be v pi hat when you have only an estimate of the value function and you refine it successively. Okay, so we see that the algorithms from the previous chapters can be expressed as follows. So whenever you face a state S, then you update its value slightly in the direction of the target, where the target can be either the full return of the episode, the next reward plus bootstrapping term, or the expectation of the next reward and the next value function, either the true one or the estimates if you don't have the true one. Okay, so we see that this, I'm repeating what I mentioned earlier. We see that whenever we face a state st and we've observed the associated target, we shifted the estimated value of state st slightly in the direction of the target for that state st, and for all other states, all states not st, then the estimate doesn't move at all. But now, when using approximation, whenever we will encounter a target, then we will slightly modify the value of our parameters, W, based on the new target, so as to have the estimated value of our state S shifted slightly towards the target. But however, when we do this, we will not only, when we change the parameters, we not only update the value of states, the state st, but changing the parameters will also update the value of many other states. Okay, so it's not possible to estimate the value of all states exactly, because there are not enough parameters to represent each state separately. Okay, so every time we update parameters, we update the value of many states at the same time. Okay, so now we've mentioned approximations of the value function, but we must determine what are good approximations. Okay, so whenever we form an approximation, we must have a way to determine if the approximation of the value function we make is suitable or not. Okay. So to assess the adequacy of the approximations designed through methods of this chapter, we will first have to specify an objective function. Okay, so we will try to optimize the policy with respect to some objective function. So now let's define what's our objective function. So for that, the textbook proposes some metric, the VE bar here, that we will define right now. So first, to define that metric VE bar, we have to define some distribution U over all possible states. Okay, so this distribution U will determine how much we care or how much we weigh the errors over the various states S. Okay, so maybe to determine how good our approximation is, well, maybe we care more about the value of some states than the value of some other states. So to do that, we must determine how we would weight the errors made over the various states. Okay, so we will define the distribution U, which is greater or equal to 0 for all states, and for which the sum across all states sum to 1. So mu is truly a distribution which will be used to weight the error made over the various states. Okay, so here to represent the accuracy of our approximations of the value function, we will quantify errors through the square differences between the true and the approximated value function. Okay, so for a state S, we will define the error of that state S as the square difference between the approximation of that state based on parameter W and the true value function for that state. So this allows us to define the objective function, which we shall try to optimize, which is the following. Okay, so sorry, a few lines ago I mentioned optimizing the policy, but what I wanted to say is not the policy, but the weights W. Okay, so here the policy is fixed, but what we're optimizing is the weight W, and we want to find the weights W which lead to the best approximation. Okay, so here for a given set of parameters W, we will define here the mean square error over all states weighted by the distribution W, which we shall denote VE bar W. Okay, so VE bar W is the, let's say, the mean square error of the approximation associated with the vector W, which is the sum across all states of the square difference between the approximated value of state S minus its true value squared, and this square is weighted by the distribution U. Okay, so when we will try to optimize parameters in subsequent algorithms, the objective function proposed by the textbook is to minimize the mean square error across all states and mean square error over the value function across all states, where the mean is calculated using the distribution US to weight the errors of all the subsequent states. Okay, so here mu we haven't said what we're going to use. We're going to discuss what the textbook proposes for mu in the next slides. Okay, but the textbook proposes to try to select parameters W, or try to learn the parameters W to form the best possible approximation of the value function so as to minimize that weighted mean square error. So what are suitable choices for mu? Well, again, there's no objective good choice, but what the textbook proposes is the following. They propose to use mu s being the fraction of time spent in state S over the long run. Okay, so if you simulate many, or an infinity of episodes, then you could calculate what's the percentage of time you spend in each respective state over the episodes, and then mu s will be the proportion of time spent in state S. This makes sense to use this distribution mu, because if you spend a high portion of time in state S, then you'd rather have smaller errors for this state because it's more relevant to your problem, so you'd rather weight it you'd rather put a higher weight to that state. Okay, so by having mu s being the fraction of time spent in state S, you put higher weights to error of states visited more frequently, which makes sense. Okay, so you penalize more heavily errors for states more relevant and more visited more often. So this mu s, it's when we do some on-policy training, this is called the on-policy distribution. Okay, so here in this chapter we have pi being fixed, but in subsequent chapters pi will be refined. But if you are in a control problem, for example, and you refine pi, then for your current pi that you use to simulate episodes and on-policy methods, then this distribution mu is known as the on-policy distribution. Okay, so it's the fraction of time spent in state S using your current policy using the policy that you currently use to generate episodes. So in the textbook, or in this course, we will focus entirely or exclusively on this distribution US. So in practice, there might be other reasonable choices for mu, but we won't discuss that here. We'll just stick with that proposed choice from the textbook. So one quick note here: if you have a continuing task where there's no end to the episode, what does this mu distribution represent? It's simply the stationary distribution of the Markov process. Okay, so you can, if you have a continuing task with like a Markov chain, for example, if you have a finite number of states, then you would simply be the stationary distribution of your states for the current policy pi that you use to generate episodes. So conversely, if you have episodic tasks which end surely at some point, then you can define eta s being the average time spent in state S in a given episode, and then in that case you can define mu s as eta s divided by the sum of eta s prime over all possible states. Okay, so the proportion of time you spend in a state S over the long run is simply the average time spent in state S for an episode divided by the average time spent in all the states. Okay, so where here the denominator, it would simply represent the expected length of an episode. Okay, because if you sum the expected time spent in all the states in an episode, well, you're gonna just find the length of the expected length of the episode. Okay, so this gives an interpretation for this mu s, and shows how to calculate it. Well, not how, but gives a representation of mu s for an episodic task. Okay, so in practice, if we wanted to calculate mu, would that be simple? Well, let's go back one slide. To calculate mu, we could simply calculate the eta s for all states, and it can be shown. Okay, again, we won't provide the proof here. So this formula, it's drawn from the textbook. We don't give the proof here, but it can be, so for these who did Markov chain or Markov process theory, you could get to the following result. It can be shown that the etas for the various states, which is the average number of times spent in a state S for a given episode, they must solve the following system of equation. Okay, so here eta S is Hs. Okay, Hs is simply the probability to be initially at time 0 in state S, plus the sum of average time across all other states, well, all states, sorry, because this can include S, of the fraction of time spent in state S prime, times here, this is the probability to transition from state S prime to state S. Okay, so here, it's not obvious, maybe I'll write it. So this guy here can be expressed as the probability to transition from state S prime to state S. Okay, so here we don't give the proof, but is there a way to understand this formula? Here, so the average time spent in state S, it's the average, the percentage of time you're in state S in the first period, plus the average time spent in state S for all subsequent periods. Okay, so this is for period 1, so this is period 1, and this is for all other periods. So how can we see this? Well, it's because for all of their periods, if you're in a state S at some point, it's because you were in some other state in the previous period and you transitioned into state S from your prior state. Okay, so here your prior state is S prime. So the fraction of time you were in state S, or the average time spent in state S, well, it's the average time where you were in some other states, and from these other states you transitioned into S. Okay, so this is what this formula expresses. So again, we won't give the proof, but if you want, you can rederive this formula based on Markov process theory by conditioning here on the previous state before joining state S. Okay. So this gives a system of equation to calculate eta S, the average time spent in the various states, and from this eta S, you could calculate mu, your on-policy distribution mentioned in the prior slide. However, we said we typically want to use approximation methods of this chapter for very, very large problems which have many, many states. Okay, so we can see that if the state space is very large, well, just summing over all states would be problematic, and then you would have as many equations as states, so solving this would simply be impossible in practice for very large problems. So this seems problematic because these etas, or the function mu, it appears in the objective function, and we are trying to optimize the parameters w to find the best approximation of the value function to minimize the objective function, and we cannot calculate the mu found in the objective function. So is this a problem? Oh yeah, and another problem, if we wanted to have that, we would need transition probabilities here, but these are also unknown in many problems in practice. So this seems to be bad news, but the good news is that in algorithms presented subsequently, we will see that we don't need mu nowhere to within the algorithms to update the values of the parameters. Okay, so to understand theoretically what we are doing in the algorithms presented in this chapter, we need to define mu, but in practice, when applying the algorithms, we don't need mu. Okay, so mu is just for understanding purposes to give a theoretical justification to what we are doing. Okay, so in practice, mu, we don't calculate it. It exists, but we don't care exactly what the value of mu is. Note here, if we go back one slide, this formulation, it applies for episodic tasks. Now, if we have continuing discounting task, then this formula has to be slightly modified. So there's some discount factor gamma that should appear somewhere in the formula. I think it's just here, but I forget about this detail, and I won't provide the detailed rationale for this, but the reason for that is discounted continuing tasks can be shown equivalent to episodic tasks, where on each period you have a percentage 1 minus gamma of transitions to some terminal state. Okay, so instead of simply discounted rewards, you can decide not to discount them, but randomly have at each period a proportion 1 minus gamma of transition to some terminal state. Okay, so if this seems a bit complicated, you can refer to the textbook about that. They will give thorough references, but I don't necessarily want to spend too much time about this because anyways we won't be calculating mu in practice, so please refer to the textbook about these fine details if you want to learn more, but I don't necessarily expect you to get that if this seems a bit blurry for you. Okay. So just know that for continuing task, instead of using equation 1, we have some discount factor to plug gamma to plug somewhere in this equation. Okay, so I'm pretty sure. Oh, yes. So probably the gamma is here because it would multiply transition probabilities by gamma, because we're assumed that 1 minus gamma of the transition probability goes to some terminal state. Okay, so I'm pretty sure here the gamma should be here for continuing discounted tasks. Okay, so now we've presented VE bar as our objective function, which we shall try to minimize when we want to find W, the best approximation of the value function. Now, is VE bar a suitable choice of objective function? Well, what the textbook mentions is right now, probably we still need some research about that, because it's not clear that this objective function is the optimal choice. For example, there's no guarantee that the set of weights minimizing this objective function would lead to a policy. Okay, sorry, give me 1 second. So, because here we're working in a fixed policy, but okay. So here we're working with a fixed policy. Okay, so this argument might not apply in the current chapter, but for subsequent chapters, we do apply control where we refine the policy. And then when we do that, we can form an approximation of the policy, and it can be shown that even if you're able to minimize VE bar, your objective function, this might not necessarily lead you to the optimal policy. Okay, so you might have policies, greedy policies with respect to your optimal value function that might be suboptimal in the sense that there might exist some other policies whose true value function is higher than your approximated, the one greedy with your approximated value function. So from a theoretical standpoint, it's not clear this objective function VE bar is the best possible objective function to use in reinforcement learning problems with approximation. But right now, at the current stage of the science, it's not really clear what alternative to that objective function would be best. Okay, so there might be research to do about that to determine suitable choices for that value, this objective function VE bar, and in what circumstances should we use it or not, and what would be better choices. Okay, but because as of now it's not clear according to the textbook what would be the best alternative, we're gonna stick with that objective function because at least it has some meaningful interpretation and it intuitively makes sense. Okay, so we want to find the weights which lead to the smallest weighted mean square error between our estimate of the value function and the true one, where the weights are respectively the proportion of time spent in each of the states. This all makes sense. This is intuitive, so we shall stick with that for the course. Okay. So typically now, instead of in our prediction problem, instead of trying to estimate the value of each state separately, we will try to estimate the parameter W to give us the most suitable approximation of the value function, where that approximation is meant to minimize our objective function, which is some weighted mean square error over our approximation of the value function. So we would like to find W star, which is such that the objective function for W star is smaller or equal to the objective function for all possible candidates W, all possible weight vectors or parameter vectors. So such a value W star would be known as the global optimum. It's the true minimum, true minimizing argument of the objective function. However, in practice, sometimes reaching a global minimum is very difficult or too complicated. Okay, so if the value function is very bumpy, has a very nasty behavior, let's say like this, then optimization algorithms might not allow you to find the true global optimum. So in that case, what do we do? Okay, so if sometimes it's very difficult to find the global optimum. Okay, so for example, if your function approximation is a neural network and W are weights of the neural network, it's typically very difficult to find the true global minimum based on this neural network. Okay, so in practice, often people will be happy with what we call a local minimum. So a local minimum or optimum is a point W. Okay, so here this is a typo. This should be W star. Okay, so it's a point W called W star where the objective function at W star is smaller or equal to the objective function for all other candidates W in the neighborhood around W star. Okay, so you might not be able to find the global optimum, but if you find a point W star which has a better value than all surrounding neighbors W, then often you will be happy. Okay, so let's draw. This is our discussion about global optima we had earlier. So if you have a function like this, And if you try to minimize it, well, maybe your minimizing algorithm might reach to this point and think that here is the true minimum, but in fact there's another minimum here. So this would be the global optimum, but this would be a local optimum. And often in practice, you can find local optimum that would work well enough. Okay, so although you would like to get to the global optimum, sometimes the local optimum will do a sufficiently good job that you don't necessarily need to reach fully the global optimum. Okay, so for practical purposes, we will try to find a set of parameter W for which is a local optimum of our objective function. Okay, so often we will be happy with that, and the algorithms proposed will typically tend to find local optima instead of global ones. Okay, but here again, so we say we will be happy with local optima, but the textbook discusses that whenever we add approximation to our reinforcement learning algorithms, unless we're in very specific cases that we will discuss subsequently, often the algorithms cannot even guarantee that you will converge to a local optimum. Okay, so the theoretical properties of convergence of reinforcement learning algorithms, when we include approximation, they're not extremely nice. You cannot have a guarantee that you will have a convergence to some local optimum unless you're in very specific cases. So for general cases, let's say you use neural networks or things like that, you might not even converge to local optima. But the point is, in practice, even if you don't reach a global optimum, if you don't reach a local optimum, if your approximation is good enough for you, it might not be perfect, but if it's good enough for your purposes, then you would be fine. Okay, so these methods often try to find very good values of parameters instead of the optimal one, and it's typically sufficient. For example, if you try to play chess, it might be fine that you get very, very, very good at chess instead of being perfect. Okay, so sometimes being very, very, very good is fine enough. And if you have a very, very good approximation of your value function, even though it's not a local optimum or a global optimum, it can be fine. Okay, so for the remainder of this chapter, we will discuss two main topics. The first one is how to use stochastic gradient methods to optimize our parameter set W, parameter set W. Okay, so again, we said we want to minimize our objective function VE bar across all values of the parameter to optimize it. But it's not obvious how to do that because, for example, we said we cannot even calculate it in practice. So how can we do that? Well, we're going to discuss that as a first topic in subsequent parts of this chapter. The second topic we will cover in what follows is what are suitable candidates for VHAT, which is suitable parametric approximations or suitable parametric functions which can work for the approximation of the value function. So we will discuss these topics in subsequent lectures. We will stop the current lecture right now. Have a nice day.